Okay, let's take a look at this one. What you need to do for this is ensure on your own that you need to draw a free body diagram. And in this particular case, the giveaway is that you are looking for the angular acceleration, and you're not given any of the accelerations of anything. So there's nothing really to relate. So you're going to need a free body diagram for this. So to start with this, what you want to do is count the degree of freedom. And unfortunately, we don't know if it's slipping here at point A or if it is rolling. And therefore, what you should do is make an assumption. And when you're making an assumption, you should create a table that shows the assumptions and the corresponding degree of freedom. So what could happen at A is it could slip. If it slips at A, the degree of freedom is 2 because the wheel could rotate, and it could also, if you stop the rotation, that's 1 degree of freedom. If you stop the rotation and continue to pull, it could slip at A. That's what your assumption is. So if you stop it from slipping, stop it from rotating, then nothing will move, and so you stop counting, and it's 2 degrees of freedom. If there's no slip at A, that's what we call roll. So the formal term for that is that it's rolling, which means no slip. And if there is no slip at A, rolling, no slip at A, then you have, it's possible for this spool to move because it can rotate, but if you stop the rotation and prevent it from slipping, then it can't move, and so the degree of freedom is 1. So problems like this, you start with the minimum degree of freedom, you make that assumption, and then you test the forces that come out because of it. Okay, so I'm going to draw a free body diagram, and I'm assuming that it's going to roll with no slip. So what I'll have is I've got this force P. I have a friction force. I don't know which way the friction force goes. I like to draw everything to the right, up, and counterclockwise when I don't know. So it's friction. All I know is that because there is no slip, the friction is less than or equal to mu Sn. I do not know that it is equal to mu Sn. I only know that it's less than or equal to. So I really don't know the direction. So I just put it in there. This is a normal force. It's a pressure basically from the floor. And then I also have a weight that's acting down through the center. So those are the forces. The next thing to do after you've drawn your free body diagram is to sum forces. Of course, you have to determine what direction you want to sum them in, and you should think about the acceleration. Because it's a body and because the body is rotating, these points have different accelerations. You need to know what point you want the acceleration of. Newton's laws, F equals ma, the A is always of the center of mass. So that's point G in this case. So what I'm going to do is I'm going to think about the acceleration of G. And if you think about what's happening, G is moving on a straight line like this. It doesn't get any higher. It doesn't get any closer to the ground. So if it's doing anything at all, any kind of acceleration at all, it's moving on a straight line to the right or maybe left, whatever. And but it's only horizontal. So because it's horizontal, I'm going to choose to sum forces in the horizontal direction, and I'm going to sum forces in the vertical direction. So here we go. In the horizontal direction, I have P positive because it's to the right, plus F, I assume, because that's the direction I drew it, so it goes in positive to the right. This is equal to the mass, and in this case it's 100 kilograms, times the acceleration of point G in the x direction, just to emphasize that I believe it's going only in the horizontal direction. In this case, I put in plus ma because I believe that the acceleration is going to the right. I'm going to solve for A, so it doesn't really matter which direction it's going. All I have to do is be consistent with whenever I plug in. So what I'm going to do is, if I don't know something, if I don't know the number, I'm going to put in that it's to the right, it's up, and it's counterclockwise. So that's going to be my assumptions. That way I don't have to worry about positives and negatives. But anyway, I put it in as plus 100A because I'm believing that it's going to go to the right. When I solve for A, if I get a negative number, it goes back to the left, or it accelerates to the left. Okay, so that's all that matters there. Let's sum forces in the vertical direction. I have minus the weight, that'd be 100, times, kilograms, so that'd be 9.81. And I have the normal up. That equals mass times acceleration in the vertical direction, and we've already noticed that the acceleration in the vertical is 0. Be careful, because it's a very common mistake for students to just say, oh, vertical accelerations are always 0. That's not true. You need to think about each individual problem, but in this case it is 0. Then I'm going to sum moments, and I know that it is possible to sum around the point A, but I'm not going to do that. I always sum moments around either fixed points or around the center of mass, and A is not fixed. It's on the wheel, and it moves when the wheel moves. So I'm not going to sum moments on that, and I'm not going to sum moments on the ground on some point, because that's not even on the body. So anyway, I'm going to sum around point G. So whenever in doubt, sum around the center of mass. Your equations will be okay. So I'm going to sum around the center of mass. Counterclockwise is positive, so that I have a right-hand coordinate system, right? So I is this way, J is this way, and the K would have to come out or be counterclockwise. So that's positive is counterclockwise. Okay, so here we go. I have P. I have a radius of, if we put it in meters, it'll be 0.25. And that is going to be a clockwise, which is negative. I have a friction with a moment arm of 0.4 meters. And that is a counterclockwise, so that's a positive. That's all that's creating moment, so that equals the moment of inertia through the center of mass. The moment of inertia is always around the point that you are taking the moments around, so that will be G. Now if you notice, they give me the radius of curvature, radius of gyration. The relationship to that and the I is equal to mass times K squared is the I. So this would be mass, 100, times the radius of gyration of 0.3, quantity squared. Those are meters, right? Yeah, meters. So that's the I times the alpha. I don't know which way alpha goes. I'm going to solve for the number, so I'm assuming it's going to go counterclockwise. You probably realize that if it's going to accelerate to the right, it's going to rotate to accelerate to the clockwise as well. Don't worry about it. You'll get the plus and the minus, and it'll tell you what's happening. Okay, so let's count the number of unknowns. I know P. I do not know F. I do not know the acceleration. I do not know N. I do not know alpha. So I have 4 unknowns, and I only have 3 equations. So at this point, students will typically panic, and they'll put a 0 in something. I don't know why, but they do. They'll tend to panic. That's not what you do. What you do is you come in here and you say, okay, let's look at the kinds of unknowns that I have, and what I'm interested in is how many motion unknowns do I have. So let's count them, right? So this one, A, is a motion unknown, and alpha is a motion unknown. So I have 2 motions that are unknown. How many should I have? What's the degree of freedom? The degree of freedom is 1. I should only have 1 motion variable. I have 2. What's going on? Oh, these 2 motions must be related to each other. That's how I know that they must be related. It's 1 degree of freedom, and yet I have 2 variables. I shouldn't have 2 variables. So, how do you know to relate? You have ropes, you have loops, and you have special points. It seems to me that special points is the thing I'm going to do. So here's what I'm going to do. I'm going to find the special points. In this case, I have A, I have G, and I could care less about what's going on up here at this point because I don't want to know, I don't need to know, and who cares, right? So I have basically A and I have G on the spool, and so I'm going to write an equation between A and G. Normally, I would advise you to write the velocity equation and then mimic it. I'm not going to. I'm just going to try to save time. But if you get confused, that would be the thing to do. I'm going to write the acceleration equation between A and G. Acceleration of G, it's a vector, equals the acceleration of A, it's a vector, plus alpha of the body they're on together, which is the spool, and I've already assumed that it was counterclockwise. You see, because I put it in right here with a plus, right, saying that I thought it was okay, I have to do the same thing here. You have to be consistent. It doesn't matter what you do, but you have to be consistent. That's why you should develop a habit to always do the same thing. Okay, so alpha K counterclockwise, that I'll get a positive if I'm right, negative if I'm wrong, crossed with the R from A to G. So from A to G is straight up, and it's a distance of 0.4. So it'd be 0.4 straight up J. Minus omega squared of the disk, or of the spool, times R, 0.4 J. And then you have all those rel terms. The rel terms are all 0 in this case because A and G are both on the spool, moving around on the spool. So these are all the terms that I have. Now, what do I know about the acceleration of A? And don't say it's 0. What you know about it is A is in temporary contact, no slip. That's what you assumed. There's no slip, right, that is rolling with the ground, right? I gave you a table that says the velocity of a temporary contact, no slip, is the same, but the accelerations are not. The accelerations for temporary contact, no slip, are that the accelerations in the plane direction, which in this case is horizontal, are the same. So the acceleration of A horizontally is the same as the acceleration of the ground horizontally. So let me put that in. So the acceleration of G, and we know that that's only in the I direction, right? So up here, remember, the acceleration was only in the I, equals the acceleration of A. All I know is that horizontally, the acceleration of A is 0. So that means that this could be AA, and there could be a vertical component, for all I know, right? And then let's do the cross products. So 0.4 times alpha. K cross J is a minus I. And then I have this minus 0.4 omega squared J. Okay, so now I'm going to pull off terms. So on the left-hand side, I have an I have an AG. On the right-hand side, I have a minus 0.4 alpha. On the left, I have 0. And on the right, I have AA minus 0.4 omega squared. So here, let me just point out a few things. This is the fourth equation that you need. Right there. It relates the alpha to the AGX. I guess I need to put an X on this guy because that's what I did up above. Okay. So it relates the alpha and the AGX. How did I know that that was the case? Because there were two motion variables, but only one degree of freedom. There should have not been two of them. And then the other thing is right here. What this tells you is if the spool is rolling, if it has an angular velocity, if it's rotating, it will have an acceleration of point A in the vertical direction. So be careful. That's why I gave you that table of things. Now, how will you know if your assumption is valid? Well, what you're going to do is you're going to calculate the friction. Friction is, and you're going to get a number. And then you're going to write what is the maximum friction. The maximum friction that you can get is mu s n. Right? And then what you're going to ask yourself is, you're going to take the absolute value of F, because the only thing the negative sign tells you is that you drew it in the wrong direction. So what? Okay, you want the magnitude. Is the magnitude of the friction less than or equal to mu Sn? If it is, then you're correct. It rolls. If it isn't, then if F is greater than mu Sn, then you say, aha, I'm wrong, and it slips. Let's go back and see what would happen if it slips. Well, if it slips, let's see, we'll use this one. If it slips, if you now know that it slips, then it's going to be 2 degrees of freedom. And when you come down here, you're going to say, okay, what is this friction force? Well, the friction force is now equal to mu Kn because you know it's slipping. The only thing that you'd have to worry about is take a look at whether your friction was plus or a negative, and that would tell you whether or not you've got the, when you drew the friction force in here, whether or not you drew it correctly or not. And so you just make sure that you have it pointing in the correct direction, because now you know that the number for it, and so you better also have the right direction. So just pay attention to that. But basically then this friction force is no longer an unknown, and so what's going to happen is your unknowns are going to be the normal, the acceleration of g in the x direction, and you'll have an acceleration of alpha. So you'll have 3 unknowns, and you'll have these 3 equations. What happens to this special points equation? It doesn't exist. It isn't there. Why? Because it's 2 degrees of freedom, and you should have 2 accelerations. The alpha and the AG are not related to each other because it's slipping. So actually, the slip problem is actually a little easier. You don't need that the special points equation, and you only have 3 to solve, and it comes out much quicker. So that's the solution to that. I also show in Mathematica, which is posted, how to actually get numbers for this guy as well. Okay.